All right, so let's go over some step-by-step kind of instructions for doing Lewis dot structures. So, step one, this is always what you want to do. You always have to do this. Count the number of valence electrons. So what I mean by that is, let's just say we took SO2 as an example, sulfur group 6, oxygen also in group 6, but there's 2 of them. So if we make that look algebraic, it would be like 6 plus 2 times 6, and that equals 18 valence electrons. All right, so now moving on to step 2, we're going to write our atoms and connect with single bonds. Our first atom listed here is going to be our central atom. So it would look just like that. We wrote it just with our single bonds. Next, go ahead and complete with the octet and then count your total electrons. So just go ahead, complete your octet just like this and see how much it gets you. See where you're at. We get 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So notice how we have 20 electrons here. Notice that's too many electrons. We wanted 18 electrons. Anytime that this happens, we're going to go back and make a double bond, possibly a triple bond if we need to. All right, so whenever we go back, we just wrote our single atoms. If we started from scratch, it'd be just like, all right, instead of doing all single bonds, I did a double bond. Now go in, fill in the octet. That's what we have right there. All right, so notice we have 18 electrons. That's exactly what we wanted. All right, now let's go through and find the formal charge and then find some resonance. Formal charge will help us find resonance. All right, so to find the formal charge, you're going to take the group number of that atom and subtract it from what's surrounding it. So if we took this oxygen over here, for example, we know oxygen's in group 6, subtracted from 4 electrons that surrounded, plus 2 bonds, so that's 6 minus 6. So this oxygen has a formal charge of 0. What about this sulfur over here? We see it's 6 minus 1, 2, 3, 4, 5. 6 minus 5 equals a positive 1 charge over here on the sulfur. And then this oxygen over here, 6 minus 1, 2, 3, 4, 5, 6, 7. So that gives it a negative 1 charge over here on the oxygen. What we want to ask ourselves is there any way we can possibly reduce these charges to 0? This will help us find resonance structures. One way we might be able to do that, let's try some things. Notice how if we try doing 2 double bonds, we notice that everything's octet is completed, but this only gives us 16 electrons. So that's not technically correct. So what we might need to do is keep a lone pair on sulfur, and you might be saying, well, doesn't that break the octet on sulfur? Hold on a second, I'll explain. And really what it's like we did here, it's like we took our original example we had, we took one of those lone pairs and turned it into a double bond. So we didn't get rid of anything, we didn't reduce it by any amount of electrons. It still has the exact same amount of electrons. If we check 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons, this just like this one. And now if we check the formal charges, we notice this oxygen still has a formal charge of 0 because it didn't change at all. This sulfur is now 6 minus 1, 2, 3, 4, 5, 6, which gives it a formal charge of 0. This oxygen is now just like this oxygen and also has a formal charge of 0 now. So we were able to reduce the formal charges to 0. And this would be the preferred structure. Now, just like you still might be saying, but isn't sulfur breaking the octet? Well, if it's in period 3 and below, it can break the octet. So if you're looking at your periodic table, elements in period 3 and below can break the octet. If it's in period 2, so like for instance, if this was oxygen, we couldn't necessarily do that. And I'll show you oxygen in just a second. But the reason why period 3 and below can break the octet is because d orbitals come into play. And so if you think of doing your electron configurations, you might remember drawing this kind of cheat sheet, or you might have seen this before, 1s, 2s, 2p, 3s, 3p, 3d. So notice how period 3 and below, the d orbitals come into play. So that's why period 3 and below can actually break the octet, and you see sulfur here breaking the octet. So now if we draw the resonance structures of these, it would simply just look like this, where we have our original example, with the partial positive and the partial negative on it. We could also flip that, because if you considered this oxygen A and this oxygen B, this would technically be a different structure, but they're essentially the same. And then you have our preferred structure over here. And it's our preferred structure because all the formal charges are 0. Like I said, I would show you what it would look like if we did O3 instead. So if we did O3, we have our original example just like we did, where we have the partial positive, partial negative, looks just like SO3. What if we tried to do the double bond and keep the octet, and then put a lone pair on oxygen here, just like that? We can't do that because oxygen is in period 2, so oxygen cannot break the octet rule. So that means oxygen has to look like this down here. So that would be our answer here. If this was sulfur, anything below, then it can break the octet and it would look like our example where we had the 2 double bonds on each side. All right. Now we're going to move on to some other examples.